Okay, thank you everyone for joining. Today we are very happy to have Tracy Slatyer. Probably butchered last name, but
No, you did it pretty well, actually.
So it's a pleasure to have Tracy. Tracy is a world expert on dark matter, and she was actually a student here at CFA, and then did a short course of IIS, after which I think joined the MIT immediately, right?
Yeah.
So so it's a real pleasure, and thank you very much, Tracy.
Yeah, well, thanks very much for the invitation. I'm very happy to be here. I flew back from Australia 1 week ago today and appear to have caught a cold on the plane, so I apologize if I have a cough. We'll try to keep it under control. All right, yeah, so I was asked to give you guys a bit of a review, an overview of astrophysical searches for dark matter and searches for indirect detection, so the standard model of particles produced by dark matter interactions out in space. I understand you've already had one talk in this series about dark matter, so I'm not going to spend a lot of time on the baseline evidence for it. Please do ask questions as I go. I guess if you're going to be monitoring Zoom, if people on Zoom have questions as I go, please just go ahead and ask. I've tried to keep the number of slides somewhat manageable, so there's plenty of time for questions and discussion if people want. All right. So knowing that you have already had a talk on dark matter and that some of you think a lot about dark matter, some that I assume not all, I wanted to start by just a little bit of a recap of things that I think define the dark matter problem for me, which is that we've got the standard model of particle physics. It's been really successful. It's really good at predicting what we see at the Large Hadron Collider and in pretty much every experimental situation we've been able to study so far, but it doesn't have a candidate for dark matter, and adding some kind of dark matter component seems, at least in my view, to be the simplest by far way to explain a fairly wide range of astrophysical and cosmological observations. What we mean, the requirements for a dark matter candidate are that we need something that is stable on cosmological timescales, that doesn't have much in the way of interactions, and in particularly doesn't interact through electromagnetism at anything close to the strength of ordinary charged matter. And it needs to be cold or warm rather than hot, just in the sense that it's not traveling at relativistic velocities when structure forms in the universe. Because if it was, you would wipe out structure on small scales and the evolution of the galaxies would look really different to what we observe. So there are a lot of ideas for what that could be, but this set of properties is already enough to tell us that none of the particles within the standard model can meet these criteria. Our stable uncharged particles in the standard model are neutrinos, and they would be hot dark matter. They would be sufficiently fast moving during structure formation that the structure of galaxies and galaxy clusters would look really different. Now, that doesn't mean necessarily that the dark matter candidate would not be something that we already know about. The most discussed possibility along those lines is probably that dark matter could be tiny black holes left over from the very early universe. That's a viable possibility, as far as I know. I'll say a little bit more about the observational constraints on that later, but there's about a 6 order of magnitude wide mass range where this is observationally totally fine. That said, in order to get this to work, you would need to form these black holes well before the first stars form, very early in the universe's history. We know the dark matter was already around when the universe was about 300,000 years old. So that requires some physics that we currently don't understand in the early universe. So I think the statement that to explain the dark matter problem, if you need some kind of physics that we don't currently understand, is pretty robust. So to me, that makes it one of the most powerful pieces of evidence that the standard model is not complete, that we are missing some important things. And so, of course, particle physicists are very interested in this puzzle as a possible clue to what we might be missing, might be going on. But every positive piece of information that we've got so far about the dark matter has basically come from looking at its gravitational effect, which means trying to infer how it's distributed through the universe and using that to make inferences about its properties. So what I want to do in this talk is first say a bit about what we have learned in more recent years and what we can still learn by just inferring the distribution of dark matter from its gravitational effects, and then talk about what more you can do if you look at the possibility that maybe dark matter could interact directly with standard model particles and not through gravitational effects. Gravity is a pretty weak force. If you have a force if you have interactions other than gravity, it's generally much easier to see.
Do you think that the negative results from particle physics experiments, the deep lines and so on, are constraining in an important way, or are they?
I mean, they're certainly constraining on individual, they're certainly constraining on specific scenarios for what dark matter could be as a particle. I mean, there are a bunch of scenarios that we can rule out based on the null results of those experiments. Fortunately or unfortunately, I think the space of possibilities is really big, and there's a lot of particle physics possibilities that are not yet really constrained by those experiments, including, I mean, I'll say a bit later, even things like sort of classic WIMP dark matter, I don't think we have really properly, we certainly haven't ruled it out. You could argue about to what degree it's constrained. That's sort of a question about how you define WIMPs and how you define a measure on your parameter space of WIMPs is how much of that parameter space have we ruled out. But we definitely have not ruled out all the parameter space. Although I'll give you an argument later that there are maybe some sort of broad questions that we could answer on the timescale of the next 10 years. But even if we answer those questions, it seems to me very hard to rule out the possibility that dark matter is some kind of new particle experimentally, unless you do it by explaining the dark matter puzzle some other way. Right? If you were able to observationally establish that 80% of what we call about dark matter is primordial black holes, then you might say, I'm just going to bet that it's 100%, and probably we don't need an extra particle.
Is it possible that something like I was wondering that there might be different explanations for different, dark matter, it's a collection of observation, right?
Right.
So what do you think?
So I think the Occam's razor hypothesis is that there's probably one answer to most of the observations, but of course it doesn't need to be true, right? Occam's razor is a guideline; it doesn't always give you the right answer. I think that the cosmological observations look very consistent with each other, and I'll say a little bit more about that later. In terms of things like galaxy rotation curves, I think it's once you put in the dark matter to get the cosmological observations right, it's relatively, at the level of theoretical uncertainty of our simulations, which is not tiny, then everything looks pretty consistent with what you would have already put in to get the cosmological observations right. So then I don't think there's any strong need for there to be multiple components explaining different things. But yeah, it could be, sure. All right. So this slide is going to have a lot of text, but I wrote it down because I think it's sort of general. It's good to have this sort of general structure in mind for what we can hope to learn by getting better measurements of how dark matter is distributed through the universe. So again, every positive statement that we have about dark matter, this is how much dark matter there is, this is how it behaves, this is how fast it's moving. All of this comes from just trying to look at how dark matter is distributed through the universe, which we learn by looking at its gravitational effects on visible objects. So you can ask how much further can you push this? If we can better map how dark matter is distributed through the cosmos in both space and time, then what can we learn about it? So you can try to learn this via the gravitational effects of dark matter on stars, on galaxies, on gas clouds, just looking at how visible matter is distributed and using that to figure out what kind of gravitational potential it's in. You can use it by gravitational lensing, so that's just looking at the effects of the gravitational potential on light. You can learn about it from the cosmic microwave background radiation, which is a tracer of structure on large scales, or from other traces of large scale structure, like just how galaxies are distributed through the universe. So that's been pretty successful so far. Getting this question of how dark matter is distributed through the universe, it's important as an input to other dark matter searches. If I want to look for dark matter particles bouncing off underground detectors in the Earth, it would be nice to know how much dark matter there is around our solar system. It's important I mean, to me, it's just interesting in its own right. We think 84% of the matter in the universe. It would be good to know how it is distributed and where it is. And that is a question of which we do have some observational access. And you can also use it to try to make inferences about what the properties of this stuff have to be. So some things that you can do with this kind of observation. You can set limits on the primordial velocity that dark matter attained from the early universe. So this is the hot dark matter argument. If dark matter is going too fast, when structures start to form, then small structures will become gravitationally unbound. So if you try to measure smaller and smaller structures and eventually you start seeing that there just aren't any anymore, that cutoff can tell you about a scale. One possible source of that scale is primordial velocity from the early universe. That's not the only possible source of such a scale. There could be new scales coming from dark matter particle physics. The most common things that people talk about here are either like the mass of, so you could have something associated with like the mass of individual dark matter particles, one possibility. So if my dark matter is primordial black holes, again, then individual dark matter particles, the individual black holes, could potentially be large enough to see with gravitational lensing probes. Okay, so that's a scale that is set by the intrinsic nature of the dark matter. At the other end of the mass spectrum, the other possibility is that the wavelength, I mean, there are a bunch of possibilities, but this is the other one that's often considered. There could be a scale set by the wavelength of the dark matter. So de Broglie wavelength goes like 1/mv. If the dark matter mass is sufficiently small, that wavelength could actually be macroscopic. So if that wavelength is macroscopic, then you will get modifications to the dark matter distribution. Particularly, it's hard to have much structure on wavelengths smaller than the size of the on scales smaller than the wavelength of the dark matter particle itself. That's often called fuzzy dark matter. The challenge here is if these scales are large enough to be observable, if dark matter is some kind of new particle at the mass scale of the W boson or the Higgs boson, its wavelength is not going to be observable on any astrophysical or cosmological scale. So, but at opposite ends of the mass spectrum, either at very high masses where the mass is large enough to be potentially observable, or the mass is small enough that the wavelength becomes macroscopically significant, you can potentially get a handle on this from the distribution. But there's about 90 orders of magnitude between those two mass points, and between those, often there's not an observable scale in the problem. You can another possible determinant of new scales in the problem is non-gravitational interactions that involve a significant fraction of the dark matter particles. These could be due to dark matter particles interacting with each other or with new particles. Like if there's also some dark radiation component, dark matter interacting with that can change its distribution, or if dark matter interacts with standard model particles, that can modify its distribution. And, I mean, I guess you could put this in the category of forces, but you can also, if the dark matter is sufficiently light and its number density is high enough, you can tell from its structure whether it appears to be experiencing Pauli degeneracy pressure, so whether it's a fermion or a boson. Okay. This is, as far as I know, basically what you can learn from looking at the dark matter distribution. Properties that are not on this list are going to be somewhat hard to get at. Also, when I say these non-gravitational interactions would have to involve an order 1 fraction of dark matter particles, these limits tend to get a lot weaker if only a small fraction of the dark matter has whatever property you're looking at here. Like if 1% of the dark matter has an enormous wavelength on the scale of galaxy clusters, that's very hard to see, because when we measure the gravitational pull of dark matter, what we're mostly measuring is the distribution of the bulk component. If there's a small component like neutrinos we think are about 1% of the dark matter. That's kind of on the boundary of what we can typically hope to measure with precision observations. Okay, so on one hand, there's a big class. So on one hand, these are all useful things to know. They're what sets some of our most robust bounds on the properties of dark matter. But on the other hand, there are a lot of dark matter scenarios that only differ on unobservably small scales, presently and probably in the medium-term future unobservably small. And so they're going to look completely degenerate under measurements like this. So when we talk about the collisionless cold dark matter paradigm, that mostly means the class of measurements that all look the same and thus make like fairly robust predictions for the distribution under these kinds of probes. All right, so we'll come back to those collisionless cold dark matter scenarios later, talk about how you might get to them. And the strategy for looking for them is mostly, okay, the distribution is what it is, check that the distribution looks like you would expect from this degenerate regime, and then look for its non-gravitational interactions with standard model particles where you can get more sensitivity. Okay, this all makes sense so far? All right.
Perhaps you can say okay back
yes. Let's get rid of that. Good. Okay. All right, so more text. Now we show the fun. Okay, so one general thing, but we're going to talk about these distribution measurements. So one distinction that I sometimes find useful to keep in mind when thinking about cosmological and astrophysical probes of dark matter is the small versus large scales. So we live in a universe that is really isotropic and homogeneous on large scales, as everybody who's taken a general relativity class knows. So on large scales, deviations from isotropy and homogeneity tend to be small, and we can predict them pretty well. So the way that we prove the distribution of matter on large scales is classically through the cosmic microwave background and through other traces like cosmic shear, is gravitational lensing of large-scale structure. Distant galaxies can act as traces of large-scale structure, so that you don't care what's going on inside the galaxy, you just care about, where are the galaxies, how many of them are there. That'll let you map out the large-scale structure of the universe. Because on those large scales, the universe is pretty close to homogeneous and isotropic, you could effectively use cosmological perturbation theory and effective theory methods. You can do analytic and semi-analytic predictions for what the signal should look like as you change the underlying dark matter physics. So this allows for pretty precise theoretical control. If you want to do any kind of measurement that is sensitive to what is 1% of the dark matter doing, or what is like just a small fraction of the dark matter doing, you have to use this kind of observation. Because you need precision to be able to have sensitivity to small fractions of the dark matter doing something. On the other hand, these large-scale probes are not always the best way to get sensitivity to a large fraction of the dark matter doing something really surprising. So, for example, if we want to look at small scales, that usually means that you're looking at the distribution of dark matter within often virialized gravitationally bound structures such as galaxies and galaxy clusters. Now, the difficulty here is that these systems are hard to model theoretically. Everything's very nonlinear. You can't do cosmological perturbation theory, or it's hard. So this typically requires some fairly in-depth simulations. You also often can't make the assumption, well, most of the universe is the dark matter, most of the matter in the universe is dark, so let's not just worry about the baryonic matter. You may have to take into account things like how many supernovae went off in the center of this galaxy over its history, because those processes can move matter around, they perturb the gravitational potential, and hence also the distribution of dark matter. So theoretical predictions in this regime are really hard. That said, these regimes allow you to probe much smaller scales. If what you're looking for is new physics that comes in at a particular scale and modifies the distribution of dark matter, you want to be able to look at small scale objects. These typically are also the regions where you achieve the highest densities. That's important for questions like, is the dark matter experiencing Pauli degeneracy pressure? You want to look at high densities for that. Or does the dark matter do dark matter particles have some kind of interactions with each other? So these kinds of systems inside galaxies are where we get the best constraints on those types of properties. Okay, so those
models are you doing now?
Sorry?
So what models are you looking at?
Yeah, so right. So again, usually these are all fairly generic statements, but I mean, dark matter self-interactions would just be if dark matter, so if it's to get meaningfully, I'll say a little bit more about this later, but to get meaningful sized dark matter self-interactions, usually people are thinking about some kind of new dark sector where there's the dark matter, but also some kind of new particles that mediate forces between the dark matter. The reason for that is just, as you'll see, the self-interactions need to be pretty large to be observable. And so like the standard model weak interactions are not sufficient, for example. the question about like Pauli pressure is the dark matter some fundamental fermion? You can put a pretty general constraint, which I will mention on if the dark matter is too light, its number density becomes too high in dwarf galaxies, and that tells you that it can't be a fermion, it must be a boson. Okay, so these are just, at the moment we're still trying to just sort of understand what are general constraints that we can have on the space of dark matter scenarios.
Maybe you're going to talk about this as well. It seems pretty obvious, how I look at the large scale distribution. I just look at a bunch of galaxies using my classical telescopes. I mean, what's the current state of the art for understanding how dark matter could be distributed within, for example, the Milky Way?
Yeah, so I am going to talk about this. I think Gaia is the state of the art. All right.
Is it true that the cosmic microwave background fluctuations can't say anything about primordial black holes, about this idea of if you have enough primordial black holes to make a difference in current, would you see its effects in CFD?
In general, the answer, right. So it depends on the mass of the primordial black holes. If the mass of the primordial black holes is sufficiently heavy, there's a part of parameter space where not the black holes themselves, but matter accreting onto the black holes would produce radiation, which would impact the CMB. That happens, I think, for black holes around a solar mass in mass scale, which are also quite constrained by gravitational lensing and by looking at how the presence of those black holes would disrupt various astrophysical systems. The mass range where black holes could viably be all the dark matter are cases where the black holes are around asteroid mass. At that mass scale, we expect there to be almost no effect on the CMB. So it's just, yeah, like the length scales that are relevant to them are not length scales that we can observe with CMB data.
Just to supplement that briefly, there's also a few orders of magnitude that can be constrained not by the fluctuations in the CMB, but the actual spectrum of black body radiation.
Yeah.
You would get disturbed.
Yeah.
Disturbed that for like 4 hours.
Yeah. All right. So those are general principles about gravitational probes. Let me show you some actual results. All right. So I said that one thing that you can look for is just the suppression of power on small scales. So this is a plot from a paper from last year, and the particular model isn't that critical here, but I'm just pulling it out for an example. I think this one is actually dark matter interacting with standard model particles. So what this is showing is the perturbation to the power spectrum of structure relative to the CDM case for cases where some fraction of dark matter undergoes interactions that suppress the structure at small scales. So the blue line is, the blue line is where 100% of the dark matter is interacting, and you basically just wipe out all power below some scale. And then if only a small fraction of the dark matter is interacting, then instead of this complete suppression, you get a plateau. So this is, again, just an example of what I was saying earlier. If your diagnostic is this, that you just lose power altogether below some scale, then you don't need a high precision observation to be like, there is no more structure at this scale. You're not trying to measure percent level differences in the amount of structure. So to study this kind of scenario, you probably want to look at relatively small scales because the thing that will make this difficult to measure is that this cutoff is only happening at a very small scale. So you'll generally get the best sensitivity from systems that let you probe the smaller scales. If you're in kind of this plateau situation, this could be difficult to see just because there's not very much of a change from on either side of this transition. So for that case where the scales are much larger, but the effect is much smaller, that's a case where observables like the CMB or large scale structure can be important. So this is using an example of a case where the thing imprinting, so this plot is showing the case where what's imprinting the scale is the wavelength of the dark matter. So x-axis here is the ultralight dark matter mass. This goes from a scale of 10 to the minus 18 electron volts on one end to 10 to the minus 33 electron volts on the other end. For calibration, we think the heaviest neutrinos are about like 0.1 eV. So this is really, really light new particles. And this y-axis is showing what fraction of the dark matter could be in this kind of state. So on this, over on this side of the plot, these constraints are coming actually, not even from galactic scales, really. These area 2 constraints are coming from observations of a star cluster, saying that if the matter had a wavelength that was comparable to the size of this star cluster, then the distribution of the stars would look different. This BHSR is a black hole superradiance constraint. This constrains new light bosons that have wavelengths comparable to the event horizons of black holes. You can get superradiant effects there. Around here, you have a series of limits. This MW thing is looking at Milky Way satellites, so looking at sort of the smallest dark matter objects that we can observe in the Milky Way and observing that they're there. So you can't be wiping out structure on too small scales. And then as you move to these smaller mass scales, so that corresponds to higher wavelengths, that corresponds to modifications of the power spectrum on larger scales. DES, BOSS, these are large scale structure constraints, as is the CMB. So these, can constrain, as I said before, about sort of a % level fraction of dark matter experiencing this power suppression.
How do you rule out 100% of dark matter from these particles?
Yes, down to at masses below about 10 to the minus 18 eV. So if you just care about 100% dark matter, you should just look at this line here. And I guess technically this cuts off at 10 to the minus 33 eV. This would also be ruled out. This is like dark matter has a wavelength longer than the size of the universe, I think. But yeah, so basically if you go to mass scale, so what this says is that if you want to evade all the constraints, all these limits, your dark matter should be heavier than about 10 to the minus 18 eV. And this is our roughly model independent lower limit on how heavy the dark matter can be. All right, so that's one thing that you can learn. You can also, we use the example of dark matter mass here, but anything that imprints a scale on the power spectrum will be constrained similarly by the same kind of observations, right? So we said before that things that could cause that were primordial velocities or interactions. So just dealing with this case of how do you get the smallest scales, there's an active research effort at the moment just to measure the smallest dark matter halos. The current threshold of the dark matter halo, so a halo is just a gravitationally bound dark matter object. The current threshold is around 10 to the 7 to 10 to the 8 solar masses. This is not coincidentally right around the threshold where halos attract enough visible matter to them to form stars. So by saying we want to measure dark matter halos smaller than this, we're also trying to measure dark halos that don't have any stars in them. This is intrinsically difficult because the way that we normally measure the properties of things is that we look at the stars, the visible traces, and use that to map the gravitational potential. If there aren't any stars bound to the object, then basically your choices are you need to find traces that are not bound to the object. So the two strategies that have gotten a lot of attention in the last couple of years for doing that are looking at stellar streams where a dark matter halo passes through them. So the idea here is you have this sort of linear trail of stars. As a dark matter subhalo goes through it, its gravity will perturb the stars, and so you get a distortion in the pattern of the stream. So that, and the other thing that you can do is gravitational lensing, which again is just using light. We can also just try to observe the faintest dark matter systems that we see that do have stars in them, and use probes like the Lyman alpha forest, which probes the clumpiness of just neutral hydrogen. So you can use gas as a tracer, even where you might not be able to use stars. This is a plot from one of those papers. This is focusing on the case where it's a primordial velocity that gives you the structure suppression. These blue data points are showing estimates of the amount of dark halos from stellar streams. So looking at gaps in stellar streams where they think a dark halo has passed through. So you have these two data points corresponding to halo masses around 10 to the 7 to 10 to the 8 solar masses, and then some just limits as you go to even lower scales. And these red points are coming from observations of classic satellite dwarf galaxies of the Milky Way. And then these orange lines are showing if you assume that the dark matter was coupled to the standard model in the early universe, was exchanging energy with it, then its mass determines basically how fast it would be going as a rate of that heat exchange. Lower mass particles go faster if they have the same kinetic energy. This is a rough estimate, but you can get about right. So then these different orange lines are showing the scale suppression that you would get for dark matter around the keV scale in these circumstances. And you see that if it's below a few keV, then you would be inconsistent with these observations. So you can put all these observations together. They're all in about the same place at the moment. They all tell you that dark matter that is lighter than around 5 to 10 keV should not have been heated up by the standard model in the early universe. And if you have other scenarios where the dark matter had some significant primordial velocity, you can similarly use those constraints to bound those. So this is just what I was saying before. If you have warm dark matter, so what we learned from these kinds of observations are your dark matter should be heavier than about 10 to the minus 18 to 10 to the minus 19 electron volts to evade all constraints. If you don't believe some of these constraints, for masses below about 10 to the minus 21 eV, there are multiple complementary constraints, so it's harder to get out of any one of them. So between sort of 10 to the minus 21 and 10 to the minus 19, you probably only need to get rid of 1 or 2 constraints to be okay. Similarly, if you warm dark matter that was populated via thermal equilibrium with the standard model in the early universe, you'll be heavier than 5 to 10 keV. So once you make these additional model-based assumptions, you can get much stronger constraints than the generic model-independent bound. And another thing that you get from looking at these dwarf galaxies is that if you look at the dark matter phase space density in these systems, it tells you that if dark matter is lighter than about the keV scale, it also needs to be a boson because the number density is too high for it to be a fermion. All right, so these things are the kind of things that we have currently learned from looking at distributions. So that we could also look at the case of, rather than sort of fuzzy dark matter halos, just look at very small and compact dark matter objects. So you could think of these as clumps of dark matter, or these could be individual dark matter particles if they're heavy enough based on gravitational lensing and their effects on the evolution of astrophysical systems. So for example, this could mean if you have lots of black holes flying through the galaxy, sometimes they will disrupt weakly bound stellar systems when they pass through. If you see a lot of weakly bound stellar systems, you can put an upper limit on how much there was in the way of black holes. So this is sort of the primordial black hole status plot as of a couple of years ago. I don't think that much has changed in the last couple of years. So if you go to primordial black holes, which are the maximally compact dark matter objects, then this region between masses of about 10 to the minus 10 solar masses all the way up to galaxy scales is excluded by a combination of gravitational lensing bounds and from cases where the black holes would disrupt the evolution of astrophysical systems. Then down at even lower masses, and this is unique to primordial black holes, you would get Hawking radiation, and that Hawking radiation would be observable if the dark matter is lighter than about 10 to the 15 or 10 to the minus 15 or 10 to the minus 16 solar masses. So there's this allowed window, this green window, where primordial black holes could be 100% of the dark matter. If instead you say, what if it's not a primordial black hole? What if it's not point-like? What if I have some kind of just like extended object, some large clump of dark matter? The constraints get weaker very fast. I mean, I told you before that the dark matter halos that we can observe are like 10 to the 7, 10 to the 8 solar masses. That's as low as we can go. If you say it's a point-like object, you can get all the way down to 10 to the minus 10 solar masses with gravitational lensing. That's what being extremely highly concentrated buys you. So as you go back in the other direction, you make it less point-like. You lose sensitivity. I said that you could use this to set limits on dark matter interactions. So what can you do with this? So there have been a bunch of galaxy studies trying to look at interactions between dark matter particles that don't necessarily involve the standard model. So the basic figure of merit here is what fraction of dark matter particles would interact with each other over a dynamical time. So if the cross-section for interaction is sigma, the number density of dark matter particles is NdM, the typical velocity is v, of collision is v, and tau is like the dynamical timescale of the system, then this fraction is just given by this product. And you could rewrite this, the number density of dark matter is determined by its mass density, which we can measure reasonably well, and the mass of individual dark matter particles, which we don't know. So then you would say, okay, this like mass density of the dark matter, dynamical timescale of the system, typical velocity of particles in the system. For a galaxy, we know more or less what all of these numbers are. So what controls the scale of the effects is there going to be this ratio of the cross-section of the interaction divided by the mass of the dark matter. Light dark matter has a higher number density, it's going to interact more often. So if you then say, okay, what kinds of limits can we get on this from galaxy clusters, you Well, so you typically find that this ratio needs to be somewhere in the ballpark of 0.1 to 1 square centimeter per gram to have observable effects. If you translated that into particle physics units, this would need to be like 1 over 100 MeV cubed. So for 100 MeV dark matter, that means you would need to have like a QCD, an interaction as strong as QCD between these particles for it to meaningfully affect their distribution. If the interaction is much weaker than that, the typical dark matter particle just never interacts in the lifetime of a galaxy, which means that there aren't going to be any order-1 effects on the distribution. As we said before, galaxies are not places where we can do percent-level high-precision theoretical predictions. So if only a small fraction of the dark matter is interacting, you just don't see it. So there are limits on self-interaction, but they're only generally going to be relevant where either your dark matter is really, really light, or it has a pretty strong, by standard model standards, self-interaction. So you could also just ask about limits on interactions with the standard model. Now, so this is an example plot from a few years ago of what those bands look like. This is cross-section on the y-axis, dark matter mass on the x-axis, focusing on dark matter mass sort of in the GeV range. The limit they said in that paper from looking at not messing up the dark matter distribution of the Milky Way satellites was this blue line. There are cosmological limits from the CMB and the Lyman alpha in these lines. Now, over on the right-hand side of this plot, this gray region is direct detection, which are the big underground experiments where you look directly for this interaction. This line goes down another 13 or so orders of magnitude below the bottom of this plot. So the lesson here is you can set limits on dark matter standard model interactions by just looking at how the dark matter is distributed. But if there are standard model particles involved, it's usually much more sensitive to look at what's happening to the standard model particles. But in cases where those direct detection experiments have blind spots, these observations can help fill them. Okay, yeah, so I'll say other things that you could learn. I've talked mostly about distribution in space up to now, but you could also look at the distribution of dark matter over time. So for a Big Bang nucleosynthesis, we have measurements of the abundances of light nuclei in the universe, from which we infer what happened at the time of Big Bang nucleosynthesis. So that generally sets limits on light, dark matter, and other new particles. Anything that was relativistic at the time of Big Bang nucleosynthesis would have contributed to the radiation energy density of the universe at that time. That changes the expansion history at that time. That would change BBN. Also, if you have dark matter that could collide and produce standard model particles, that would change the relative temperature of photons and neutrinos at early times, which would also have observable consequences. So what those BBN constraints tend to say is that if the dark matter was, so for cases where the dark matter was once at thermal equilibrium with the standard model, produced standard model particles through its annihilations, that generally requires the dark matter to be heavier than the MeV scale. If it's lighter than the MeV scale, you would disrupt Big Bang nucleosynthesis too much. That doesn't mean dark matter can't be lighter than an MeV. It just means that it has to be fairly decoupled from the standard model at that time. There's also been some work done on just how the dark matter content of the universe has changed over time. This is from a paper from a couple of years ago, where what they were looking at was, so this is a measure of how much dark matter there is in the universe. The gray line is just based on the present day, well, actually, really, it's mostly based on the CMB observation of the amount of dark matter in the universe, assuming that it doesn't change. And then this yellow region is showing what they got from observational constraints using the CMB at large-scale structure. And basically, the conclusion of these results is we don't really have any evidence that the amount of dark matter in the universe has changed from the CMB epoch to the present day. And we have reasonably good constraints that tell us that it has not changed by a large amount, because we have observations of the large-scale structure of the universe when the universe was 300,000 years old, when the CMB was emitted, and also basically now.
The JWST observations of early galaxies have any things to tell us about?
I don't, yeah, so this certainly wouldn't involve JWST. I don't think that JWST addresses this particular question. In JWST, you're kind of looking at the outlier galaxies. The way that you get information about this is you just want to look at lots and lots of galaxies and give you a tracer of how is the large-scale structure through the universe. This is also enough. These like limits on how much the dark matter abundance has changed. This also goes to the question about maybe, you know, different things, there are different explanations for different things that we usually call dark matter. Could it be, for example, that there was dark matter at the CMB epoch, but then it all decayed away and the galaxy rotation curves are something else? Again, this looks pretty consistent in detail. And one of the things that you can say from that is that the dark matter is decaying away into anything. The lifetime must exceed 20 times the age of the universe, which means that no more than 5% of dark matter could have decayed away from the CMB epoch to the present day.
What is that quantity omega G?
Omega G, this is just this is just a fraction of the energy density that is in dark matter. Yeah, so I need to think about exactly how it's defined, but it's the equivalent of omega dmh squared today.
Because 0.2 seems low.
No, 0.12 is there because it has the little h squared factor in it. Yeah, that's right. Okay, and so then the last question was about just mapping dark matter in our Milky Way. This is an important input for terrestrial searches that depend on the local dark matter density and velocity. If you're running these big M-body simulations and you want to understand, all right, how closely does this simulation resemble the Milky Way, it's also good to know as much as we can about the Milky Way's dark matter distribution, so you could do that matching. So typically the strategy here is just to use the stars as traces of the gravitational potential, lots of stars in the Milky Way. There's been some work to identify particular subpopulations of stars that tell you that there was a merger of another galaxy into the Milky Way at some earlier time. And mostly the tool for this in the last few years has been data from the Gaia telescope, which has made high precision measurements of a large number of galactic stars. This is just an example from one summary paper from a few years ago on what is the dark matter density at the Earth's location. From these upper ones are showing the results of relatively local measurements where you try to look at how stars in our neighborhood are moving. And then these lower measurements are based on global fits to the Milky Way. That's it. Like you will see from this, we have a decent measurement of this. The error bars are still all order 1. This is again, not a high precision measurement. Okay, so that's 40 minutes into my talk, but we have covered a bunch of shadow stuff. That's basically where I think we are in terms of mapping the distribution of dark matter in our galaxy and through the universe and what we learn just from that without making any assumptions about how dark matter interacts or does not interact with the standard model. This relies only on dark matter having a gravitational imprint.
Do you expect any information from LISA or some sort of gravitational?
Yeah, so so I guess the most striking thing from, so the LIGO results, so for gravitational waves, interesting. The LIGO results gave us some information about whether black holes could make up the dark matter of the universe. And they could potentially tell you something really interesting if, for example, like with LIGO, if you found that there are black holes that are too small to have been produced from stars. Understand astrophysics. People talk about that maybe giving you a clue as to what dark matter could be doing. I guess the LIGO results also told us that gravitational waves travel basically at the same speed as the speed of light, which constrains some modified gravity theories that are alternatives to dark matter. But more or less, I don't think we have learned that much from LIGO in this kind of direction. For LISA, what people mostly talk about with LISA is trying to get a handle on phase transitions in the very early universe. So if there was, we think that doesn't happen in the standard model, but if there was a dark sector with new particles and new forces, and there was a phase transition in that sector, that could leave an imprint, which would potentially be observable in LISA. So yeah, I think what LISA maybe gives you here is a probe on what was happening very early in the universe's history, which could potentially give you information on how the dark matter got produced in the first place. But you would have to be kind of lucky because there needs to be some reasonably violent event like a first order phase transition for LISA to see something. Does that make sense? Sure. Yeah, all right. So that's what I want to say about gravitational probes. In my remaining time, what I want to talk about is the optimistic scenario where in addition to gravitational interactions, you might have some kind of non-gravitational interaction between dark matter and the standard model. We do not know that such an interaction exists. right? I mean, we don't have any direct, well-confirmed observational evidence of this. But if we found it, it would tell us a lot about the dark matter scenario. And we've got a lot of data on standard model particles in our universe, so we may as well use it. So this is a category of searches called indirect detection. So a tentative definition would be, I want to look for signals of dark matter interactions where, unlike the probes that I've talked about so far, I do it by measuring standard model particles rather than just trying to map out where the dark matter is, and where the relevant dark matter interactions occur outside my detector. When they occur inside my detector, I call that direct detection or a collider search, right? So indirect detection, in principle, the interactions can happen anywhere in the universe so long as they're outside your detector. That has advantages and disadvantages. The advantage is your detector is very large. It's the entire cosmos. The disadvantage is that you can't control it at all. So the classic failure mode of indirect detection is, do you really understand what was happening between the interaction site and what you did the measurement? So the classic examples of indirect detection processes are you want to search for long-lived particles that are produced by the annihilation or decay of dark matter. So in many, but not all dark matter models, when dark matter particles collide, you could produce visible particles. SM here just means standard model, or the dark matter might not be perfectly stable. We said that just from gravitational considerations, its lifetime should be longer than 20 times the age of the universe. But if it decays into standard model particles, we would really, really have seen it if 5% of the dark matter had decayed into standard model particles, as I will show you in a moment. There are other mechanisms that you could look for. In some kinds of cases where dark matter is very light, dark matter could oscillate into photons under certain circumstances. That would be like just DM comes in, standard model particle goes out. You could look for that. The sort of classic way to do the search is you look for these standard model particles directly, but you could also look for downstream observable effects rather than the particles themselves. So like maybe you produce these particles and they heat up a gas cloud and you see that the gas clouds are much hotter and brighter than you would have expected. So I would also call that indirect detection. So why indirect detection? Well, you get to piggyback on all the existing multi-wavelength and multi-messenger studies of our universe, so in gravitational waves, in photons across the electromagnetic spectrum, in neutrinos, and in charged particles, which lets you test the dark matter properties over a really wide range of models and a really wide range of dark matter masses. The interactions could occur anywhere outside the detector. That means that you can probe really large time and length scales. In thermal freeze-out scenarios, which are cases where the dark matter was in thermal equilibrium with the standard model in the early universe, and then most of it got depleted through annihilation, then the strength of the annihilation is directly related to how much dark matter there is today. So you can directly probe the process that sets the amount of dark matter. This is an example of a summary plot of what the constraints are from indirect detection on dark matter decaying into standard model particles. And the exact height of these lines will depend on exactly what standard model particles you decay to, but they'll all be pretty similar. So the dark matter mass on the x-axis. This particular plot is going from 10 to the minus 5 GeVs, that's like 10 keV, up to 10 to the 17 GeV, which is nearly the Planck scale. So there are a lot of possibilities here. The pink line is the lifetimes that we expect to be ruled out with current sensitivity, such that we would have seen the particles if dark matter was decaying in the standard model stuff with this lifetime. And the thing that I want you to notice here is sort of like the weakest lifetime limits on this plot are 10 to the 25 seconds, which is about 8 orders of magnitude. So current lifetime of the universe, a few times 10 to the 17 seconds. This is about 8 orders of magnitude longer than the lifetime of the universe. So just from gravitational results, we were able to say the lifetime has to be more than 20 times the age of the universe. You can't have had more than 4 or 5% of the dark matter disappear. But if what it's disappearing into is standard model particles, that buys you something like 8 to 12 orders of magnitude in sensitivity, right? So general rule, if you can see the standard model particles, are going to be much more sensitive. These limits also are what constrain primordial black holes evaporating away through Hawking radiation. Okay, so suppose I tell you, okay, I have a dark matter model, I want to do an indirect search. What kinds of general questions can I ask? So one question is, what kind of standard model particles are you searching for? We have existing searches for photons from radio frequencies down around 10 to the minus 7 electron volts, up to the PeV scale. This can constrain dark matter at much higher masses because if you inject a really high energy photon into the universe, it interacts, it makes secondary particles. You can look for the lower energy secondaries. We've measured neutrinos from the MeV scale up to the PeV scale, protons and antiprotons, nuclei and antinuclei. These are the stable particles. We have measurements of this using ground-based experiments, cosmic ray experiments like Auger. The highest energy cosmic ray we've detected, Google tells me, was 160 eta electron volts. We can discriminate protons from antiprotons with AMSO2 up to about the TeV scale. You can look for electrons and positrons, which we measure with detectors up to about the GeV to TeV scale. It's hard to measure sub-GeV cosmic electrons and positrons out in space because we live in a solar system and the solar wind keeps them out. But we actually have some results of this because they put a spectrometer on Voyager before they sent it out of the solar system. So I actually find it very charming that some of the strongest constraints on certain dark matter models are coming from a 1970s experiment, just because it's the one thing that we have that went outside the solar system. Another general way that you could classify these constraints is where are you going to look? The photons and neutrinos, uncharged particles, they travel in straight lines, so you can look towards the galactic center, the galactic dark matter halo, galaxy clusters, dwarf galaxies, the extragalactic background. You could also do blind searches for dark matter clumps. You could look at the effects of dark matter that was captured in compact objects like stars or planets or neutron stars. So you could sort of like take the cross correlation of these two terms, and there are many, many indirect detection searches out there, and I am not going to tell you the results of all of them. But there's a nice review that I think I cited on the previous page that is relatively recent that gives a lot of these results. I will just tell you the summary of where we get to. For charged particles, because they don't travel in straight lines, generally when you look at the signal, it's not meaningful to say where did the signal come from. You're always going to be integrating just over sources within a large volume. And then the last question that you need to ask is, if you're not looking for the particles directly produced by the interactions, what are the steps between the dark matter interaction and the thing that you actually observe? What do you need to model, and how are you going to distinguish all this from the background? Okay, so that's sort of the full landscape of indirect detection searches. Let me tell you about where we are sensitivity-wise. I've already shown you the results for decays. So one goal that you might have is in these classic WIMP scenarios, the way that the dark matter gets its abundance, as shown in this famous plot from Coleman-Turner, is that, so this y-axis here is the co-moving number density of dark matter in the universe, and the x-axis is a measure of time. So the idea is that early on, the dark matter was in thermal equilibrium with the standard model through non-gravitational interactions, and its abundance was like the abundance of radiation, where the temperature of the universe was hotter than the dark matter mass. Then annihilation started exponentially depleting the abundance of the dark matter until those annihilations became inefficient relative to the expansion of the universe, and the co-moving abundance plateaued. So this means that your co-moving abundance is determined by the annihilation rate. Higher annihilation cross-section means lower late time abundance. Lower annihilation cross-section means higher late time abundance. We know what the dark matter abundance is in the late universe, so we can identify which of these lines is the right one and get a measure of what the cross-section was in the early universe. And that is this thermorelic cross-section, which turns out to be almost independent of the dark matter mass, comes out around 2 × 10⁻26 centimeters cubed per second. We said before that if you want to not mess up Big Bang nucleosynthesis, this works down to masses, dark matter masses of a few MeV. Below that, you would disrupt BBN too much. There's also an upper limit that for mass scales much heavier than about 100 TeV, you run into this unitarity bound that says it's not physically possible to get an annihilation cross-section this large. So there is a finite range of masses in which this mechanism could possibly work.
Say more about that limit.
The unitarity limit, yeah. So it's basically just if you have, when you study like scattering in quantum mechanics, you may remember expressions which are sort of like, if you do a partial wave decomposition in quantum mechanics, you get expressions which are like 4 pi over k squared times like e to the I delta L. Something like this. I mean, I may be getting the factor of 4 wrong, right? Times 2l plus 1. Right? So the statement is that for annihilation in the early universe, you have a limit on how many partial waves can potentially contribute to this. There's a So in a lot of models, it turns out that only the first couple of partial waves contribute because the others get very suppressed at non-relativistic velocities. But there's just a general argument that like high partial waves contributing corresponds to particles colliding with very large impact factors, and that can't happen in the early universe plasma because there's just like a particle separation scale. So then if you only have a limited number of partial waves, like, I mean, for simplicity, imagine that you only have the first partial wave contributing, you know, if you have the first few, then it'll change things by a factor of a few. So then what you have is this cross-section is strictly less than, right? You know, up to like there's like this is a phase factor. But yeah, I guess this could potentially be -1, so that could be true. So maybe that's factor 4, right? Or 1 factors. But so then there's this strict upper bound. So this freeze out only happens when the velocity of the dark matter becomes, when the velocity of the dark matter drops below C, so the temperature is smaller than the mass of dark matter. You can figure out roughly what that is. So if you're in the non-relativistic regime, this is m squared v squared. You know roughly what, so you could write this as the mass times the temperature, since the temperature is roughly m chi v squared, kinetic energy. So you know roughly what the temperature is at freeze out as a function of the mass. When you do this calculation, you find, because it's an exponential fall, the temperature of freeze out is pretty well determined just by getting the right relic density. And the temperature of freeze out is about the dark matter mass divided by 20. That's just, you need to go down e to the -20 on this curve to hit the right relic abundance. So then so this is just like a hard upper limit on how big the annihilation cross-section can possibly be. To get the right abundance, you need to hit this number. When your mass is higher than about 100 TeV, you cannot hit this number. Like it would violate this upper bound. I mean, essentially, but because V is basically fixed, and so this is proportional to 1 over the mass squared for the dark matter. So you make the mass too big, this upper limit just doesn't let you get the right abundance. So that means that there's a finite window in which you can in which this mechanism can possibly work. The acceptance to this, if you're willing to change your cosmological history by a lot, then you could get away from this bound. But if you don't do that, then there's only a finite window of masses where this can work. And if you ask, okay, so how well have we done at testing this annihilation cross-section of the standard model particles? So on this plot, this orange line is this thermal VM benchmark. This gray region is where you hit this unitarity bound. I mean, this is kind of crude. Like this is drawn at 100 TeV, but it might be 200 TeV or 150 TeV, depending on the model. The pink region is what we think we have currently ruled out with indirect detection. So you basically see that we hit this thermal benchmark cross-section around about 100 GeV. If dark matter is lighter than 100 GeV, then it cannot have this annihilation cross-section at the present day. We would have seen it already. Caveat, if it annihilates 100% neutrinos, then you get a bit more space. And that's mostly based on gamma ray observations and observations of antiprotons. This green region is where we're hoping to go with telescopes over the next decade or so. If they hit their sensitivity, we will have sensitivity to this mechanism over pretty much the entire mass range where it's applicable. And yeah, but basically, so I'll just say, you could look at my slides later. This is the list of specific telescopes that go into that green line. But the main thing at these higher masses is large-scale Southern Hemisphere ground-based gamma ray telescopes that can look for high-energy gamma rays, some of which are already under construction. This one's in China, which is not the Southern Hemisphere, but they could do high zenith angle observations of the galactic center and hopefully get pretty good constraints. The Cherenkov Telescope Array and the Southern Widefield Gamma Ray Observatory are both successors to current experimental technologies that would have Southern Hemisphere sites and would allow us to really have sensitivity to this thermal relic scenario over its whole range. So that, I think, is pretty interesting. As you go down to lower energies, when you think about, say, MeV to GeV dark matter, so there that thermal relic cross-section could still work. And there's a ton of effort. I gather you have a third talk about accelerator searches for dark matter. There's a lot of effort at the moment going into looking for MEV to GeV dark matter with accelerator and direct searches. That said, in all of these scenarios, you're already in the regime where indirect detection has already told you that you cannot have that thermorelic cross-section at these masses. We would have seen it already. So generally, the kinds of models that people are thinking about here are cases where either they're not produced through this thermal freeze-out mechanism, or there's some physics that dramatically suppresses the annihilation cross-section in the present day. One thing that could suppress that is when you do this, it's if when you do the partial wave decomposition, the leading order partial wave that contributes is not the S wave. That leads to a suppression of the annihilation rate at low velocities by a factor of v squared. So if that's the case, then you would not currently be ruled out for thermorelic models in this range. Next-gen experiments could potentially get astrophysicists are interested in just doing better telescopes in this MEV to GeV range because there is kind of a sensitivity gap here. This is from a plot by one of the people leading one of those experiments at a conference from earlier this year. So this is looking at sensitivity as a function of energy. Lower numbers are better here. We have pretty good sensitivity at gamma ray energies and at X-ray energies, and then there's kind of this gap in between. One of them, COSY, is already scheduled for launch in a couple of years, but there's a whole bunch of new ideas for experiments to close that gap. You could go down to lower energy still. We have X-ray indirect searches. If dark matter was annihilating or decaying and dark matter is lighter than the electron, there's not a lot of things it can decay to in the standard model. Basically, your options are photons or neutrinos. So for these experiments, often what people look for is just like a monochromatic photon spectral line. So dark matter decaying to 2 photons or to a photon and a neutrino would do this. So this is a case where really good energy resolution can be really helpful for you. The line would have an intrinsic width for dark matter in the galaxy. That width would be determined basically by the velocity of the dark matter particles. There are several current and future X-ray experiments that are targeting these fine energy resolutions. They can both look for dark matter lines, and if they had sufficiently good, and if they saw a signal, maybe even be able to measure the line width, which would be a way to confirm a dark matter origin of eight backgrounds. So you could also use X-ray observations to set constraints on like axion photon oscillations and on cases where you've got higher mass dark matter, but some of the photons that are produced are at low energies. These are just showing 2 plots. Plot on this left-hand side is showing what we've done for sterile neutrino dark matter. The simplest versions of sterile neutrino dark matter are mostly ruled out by now by a combination of these warm dark matter bounds that we talked about earlier and these X-ray constraints. This right-hand plot is showing limits on axion-like particles. So this is light dark matter that could oscillate into a photon in the presence of a magnetic field, showing limits on that from various astrophysical observations, including X-ray observations of M87 and M82. And you could keep, you could keep going. Like, this is the thing. We've measured the electromagnetic spectrum really well, and so we could use it to put constraints on all sorts of dark matter models. There are limits. You asked about JWST earlier. There are some limits on light decaying dark matter from JWST, just from the fact that it's a sensitive IR telescope. So you can look for dark matter decaying in a way that produces IR photons. Even if you have much heavier dark matter in magnetic fields, its products, if you make electrons and positrons that travel through magnetic fields, that can produce radio signals, even if the electrons are much higher energy. So that could lead to significant constraints. That said, I mean, there you do need to worry about the systematics and how those charged particles propagate and the magnetic fields that they propagate through, but it's potentially a pretty sensitive channel. All right, yeah, we should wrap up. I know we're at the end of time. So I'll just say cosmic ray, cosmic ray antimatter, we don't have to stick to gamma rays. We can look at charged particles as well. There's actually an experiment called GAPS, which is a dedicated experiment searching for anti-deuterons and anti-helium, which, from what I could tell from the internet, is meant to launch next week at the start of December. So that will be really cool, especially since AMSO2 has tentatively observed at higher energies events that look like anti-deuterons or anti-helium already. Now, that's a case where a lot of people don't really believe that detection because it would be really surprising. It's actually very hard to explain the standard model, but it's actually also very hard to explain even with dark matter. But maybe GAPS will give us some clarity on that front. And I think the last thing I wanted to mention was I've talked mostly about the sort of direct, indirect detection where you look directly for the particles produced by dark matter annihilation. But as Bryce mentioned earlier, there's also a lot of interesting constraints that you can set just from if dark matter was annihilating or decaying or otherwise interacting with standard model particles, it could change the history of the universe in interesting ways. Could heat up the universe, ionize the universe in early times, change the evolution of the first stars, modify radiation backgrounds. This upper panel is from a few years ago, showing constraints on dark matter annihilation from the Planck collaboration. It's cross-section on the y-axis, mass on the x-axis, and these different colored lines correspond to different standard model decay channels. So this is not as strong as some of the constraints I showed you earlier on annihilation, but again, it kind of acts as a backstop for mass ranges or channels where we don't have good telescopes. Just messing up the CMB sets a limit on how much power you could have injected in the early universe. And this panel is showing the green and red and blue. The green and red regions are existing cosmological constraints on dark matter decay. The blue lines are showing forecasts that you could possibly get if we measure a cosmological 21 centimeter signal, which we might do in the next couple of years. But I have a slide on that, but I'm going to skip it. Okay. So as I said earlier, I mean, there is a challenge for indirect detection that is not a controlled experiment. So there are a number of searches where we'd really benefit a lot from a better understanding of how cosmic rays are produced and propagate, the galactic diffuse photon emission, which is a background to a lot of these photon searches, and also just an improved understanding of how the dark matter is distributed through the universe, as that can tell you where to look. But yeah, so I'll leave my summary slide up there. We had a bit of questions and discussion through the talk, but if there are any more questions, I could take them now.
The photon sector that you looked at, you include hidden sector or dark photon? I mean, hidden photons?
Right. So for these indirect detection bounds, when I say photons, I really just mean like you're looking at photons. I really just mean regular photons. But indeed, like, I mean, so sufficiently light dark photons could potentially oscillate into photons. So dark photons can act as a source of visible photons that you can look for. Dark photons at a heavier mass scale probably aren't stable and won't act as like a reservoir of power themselves, but they can act as a mediator for interaction, for any of these interactions, like for annihilations, for decay, for scattering, and so you can set constraints on them through those channels. But yeah, but when I say photons here, I mean, I really just mean like you are looking at photons, and it is hopefully telling you something about the interactions.
Not that I see.
Thank you very much. Fascinating talk.
That's why the